I could start?
Yes, yes, you may.
Okay. Thank you very much for the opportunity to share our results with presentation from our institute, from our laboratory with our colleagues, with the title Consecutive Shock Wave and Fatigue Loads, Fundamentals and LSP Optimization Strategy. I would like to share with you the following content: dynamic and shock wave loads, principal differences, action invariance under shock wave and fatigue loads, experimental determination of action invariance, defects induce spatial scaling, optimization of LSP region based on action invariance, and discussion. I have PDV and it's quite easy for me to follow. First of all, I would like to attract your attention that there is principal differences between dynamic and shock wave loading. For instance, dynamic loading, it's as consecutive loading, dynamic and fatigue is very important concerning very sharp problems, so-called foreign object damage. When we have occasionally impact of some hard particle, for instance, with blades, and after that, the fatigue life decreases catastrophically. And characteristic time for this collision around 100 meters per second, and characteristic strain rates less than 10 to 4 inverse second. And as usual, after that, we could estimate a characteristic fatigue lifetime. And if you are talking about shock wave and then fatigue loads, there is principal differences. These principal differences are the following. Due to the nature of shock wave, because for characteristic time of the collision or laser induced impact, we have characteristic strain rates more than 10 to 5 inverse second. And since in this case we have shock wave with very specific rules, well known as Swiggle-Grady rules with this 4-power law, I would like to attract your attention concerning strategy. If, for instance, we have dynamic loading that is typical for foreign object damage, that presented in this slide. In this case, we have used the following way. It was realized, first of all, experiment for dynamic loading using Hopkinson bar test for standard samples, and then we investigated a scenario of fatigue life, for instance, using Shimadzu for in high cyclic fatigue regime or very high cyclic fatigue regime to analyze characteristic structure of fracture surface with quantitative analysis of fracture roughness. And I would like to attract your attention again that dynamic loading with characteristic strain rate less than 10 to 4, it's like quasi-static loading. It means that we can use, like in quasi-static, this parameter as residual stress that is typical for quasi-static and dynamic loading. Qualitative differences we have for shockwave loading, induced also by laser in the condition of laser shock pinning. Why? Because in this case, we have the formation and propagation of shock wave with this characteristic non-linearity at the shock wave front, so-called structured shock wave front, when we have very pronounced self-similarity with this power law and this power exponent. And it was, during maybe last 40 years, precise investigation of this situation with structural shock wave, and it was shown that for these conditions of shock wave loading, there is another very meaningful parameter instead of residual stress, that has the nature of invariant in shock wave action invariant that could be represented due to the multiplying of characteristic energy related to the area between equation of state of Gigonio and characteristic curve related to real loading. And this shock wave invariant can be considered as the measure of structural changes in material due to the impact. It's very important that this is namely invariant because if, for instance, you have loading of the sample with characteristic strain rate in shock, in this case we have several, for instance, particle velocity that could be reduced to some single in some dimensionless coordinates. And this self-similarity exactly corresponds to this universality of 4-power law. And understanding of this very important fact for laser for shock peening, for instance, it was very stimulating for us to develop approach to apply conception of shock wave invariant and fatigue invariant to compare and to estimate the optimal conditions that can be used for estimation and strategy of the increased characteristic lifetime of the material after shock wave processing. I would like also to attract your attention that there is very exciting similarity between cell-similar structure of shock wave, structured shock wave, and the Paris law for ductile materials. It's well-known fact that the Paris law for ductile material has the power also very close to the four. What it means, like in the shock wave front, the universality of shock wave front is a consequence of very strong collective behavior of numerous micro-shear, which gives namely this 4-power law. Similar situation we have for equation after Paris with this power law, which corresponds the collective and very strong behavior of persistent slits bands in the area that named as process zone. And understanding of this very important fact, we developed special strategy for optimization of material in the condition of the consecutive shock and the following fatigue loads. For this goal, we realized the following experiment. It was typical shock wave experiment when the target of aluminum magnesium alloy, which represent two massive targets coupled together that were loaded by explosives with formation of shock and measurement of parameter of shock wave at the oblique surface of the second target. You can see the visor registration. The second target was used namely to provide the condition of compression test in the first target, because when the reflection wave reach this area which separated two targets, we have the second reflection, and only compression wave loads we have in the first target. Then the first target was used for the preparation of the sample, standard samples that can be used for fatigue test. It's very important that in the target it was realized plate impact test. It means that whole volume of this sample were in the same conditions of loading. Then, after preparation from this cutted volume of aluminum magnesium alloy, it was obtained standard samples that were used in the condition of high cyclic fatigue and very high cyclic fatigue to reveal specific fracture surfaces both for high cyclic and very high cyclic fatigue with generation of fisheye area, area of fine grain where the crack propagates, and the final area which leads to the fracture of the sample. It was very important. Why? Because in this case, we had the opportunity to estimate both invariants for fatigue loads using traditional stress intensity factor parameters and additional parameter which corresponds characteristic area at the crack tip, which provides crack propagation. And when we have estimation of this parameter through the stress intensity factor, and when we could estimate from macroscopic test or structural studies this characteristic size of process zone, we could estimate the action invariant for fatigue loads, which includes characteristic time of crack advance. And of course, after that, when we have the estimation of shock wave invariant after play impact test and fatigue invariant, in this case, we could formulate the minimax problem for the estimation of maximal value of characteristic time of fatigue crack advance after some cycle of experiments for different amplitude of loads and of course corresponding definition of parameter after fatigue test. It means that cell similarity in terms of the universality of 4 power laws, both for shock wave loads and fatigue loads, can be used as a background to introduce invariants that reflects wave nature or non-locality nature of crack propagation to estimate characteristic time of crack advance. I think it's important from point of view of understanding of qualitative differences, the behavior of materials in the consequent loading, quasi-static and then fatigue, or dynamic and then fatigue, because shock waves preliminary loads has qualitative different conditions and physics concerning responses of materials and structure evolution during these consecutive loads. I could outline our vision of optimization methodology of shockwave treatment to improve the fatigue resistance, which could include conducting experiments with plane wave loading of targets to determine the values of action invariant of structured wave runs at different wave pulse amplitudes and obtaining standard samples for fatigue testing. Conducting fatigue tests on standard samples in combination with structural analysis methods to determine the action invariant related to the kinetic of fatigue cracks. Substantiation of models to describe shockwave runs in the characteristic ranges of LSP treatments, followed by an experimental study of the effect of this treatment for model LSP setting. And development of optimization algorithm using action invariants. I think we try to show that for shockwave and then fatigue loads, consecutive condition of loads, we need to use some very specific invariants to estimate fatigue life. Because according to our feeling, the usage of residual stress, it could be used mainly for quasi-static and dynamic test, because shockwave loading has very, very specific self-similarity features. And another very important aspect that I think we could discuss, that namely plate impact tests to realize shockwave experiment can be used because for typical condition of LSP treatment, sample or small plate, also using quasar, we have very small size of laser spot. As a consequence, it's very problematic to estimate characteristic parameter of shock wave using, for instance, Weiser system. And another artificial factor, I think, could be considered as very, very important. It's vaporization of the thin film and influence of liquid. And according to our feeling, it's really necessary if we need to estimate the realistic parameter of shockwave loading to realize standard plate impact tests and to have a representative sample according to ASTM requirements and so on, to provide fatigue test for the sample when all volume will be in conditions of shock wave loading. Thank you very much.
Okay, thank you.